Previously, we've discussed how one can go about locating the positions of various local and global extreme value points, or extrema. In this lecture, we're going to discuss the second derivative test. Now, the second derivative test is a way that we can identify whether a given critical point is a local maximum or a local minimum. So the second derivative test gives us additional information about a given critical point. The test is not always conclusive, so under certain circumstances, the test yields no information. So in those circumstances, the point can be a maximum, a minimum, or perhaps neither, just a critical point that's neither a maximum or a minimum, a so-called saddle point. So I'll discuss those circumstances in which the test gives no information in a moment, but first let's just write the general statement of the theorem. So this is called the second derivative test. So given a function f that has a continuous second derivative at the point x is equal to a. So in other words, the second derivative has to be continuous at the point a. So this test does not work if the second derivative is discontinuous. So then the following statements hold. So if the derivative evaluated at a is equal to 0, this means that it's one of the ways in which there can be a critical point at a. A is also a critical point if the first derivative is undefined. But in order for the second derivative to be continuous, the first derivative has to actually be defined at a. So if the derivative of f at a is equal to 0, and the second derivative of f at a is greater than 0, then the point x equals a is a local minimum. If f prime of a is equal to 0 and f double prime of a is less than 0, then x equals a is a local maximum. And then the case in which there's no information is if the second derivative is equal to 0. So then we get no information, because if the second derivative is equal to 0, neither of these statements tell me what type of critical point the point x equals a is. So if the second derivative is equal to 0, along with the first derivative equaling 0, then the function might have a maximum, minimum, or neither. So the second derivative equaling 0 gives us no information. So let's see why this is true. So in general, we saw that when you have a critical point, it's a candidate for, in particular, when f prime of a is equal to 0. So here's a graph of f prime. So f prime of a is equal to 0 indicates that the derivative might be passing through 0. So the derivative might be turning from negative to positive, or it might be going from positive to negative. Either way, this indicates that the function is changing direction. So if the derivative goes from negative to positive, like I showed here, then the original function f stops decreasing and then starts increasing right at the point x is equal to a. Right, so you see that. So here, so this is similar. So here's the function f. So for x less than a, the derivative is negative, and for x greater than a, the derivative is positive. The derivative goes from negative to positive. Now this indicates that the function goes from decreasing to increasing. So whenever the derivative, so if f prime of a is equal to 0, so that's basically exclusively what we're talking about for this video. So we have a function and its derivative is equal to 0. now what? So if f prime goes from negative to positive at the point A, that means f must go from decreasing to increasing, so that implies that f has a local minimum. But if the derivative is passing from negative to positive, that indicates that the derivative itself must be increasing through 0. So it's not just that it is equal to 0, it's equal to 0 and it's increasing. And if the derivative is equal to 0 and increasing, that's equivalent to saying that the derivative is moving from negative to positive. Now, whenever any function is increasing, its derivative must be positive. So since the derivative is increasing, so f prime is increasing because we're going from negative to positive, that implies that f double prime has to be greater than 0. And so whenever f double prime is greater than 0, that implies f prime is increasing. If f prime is equal to 0, f prime must be increasing through 0. So that means that f prime must go from negative to positive, which means that our original function is going from decreasing to increasing, and therefore our point is a local minimum. And then the exact opposite story is true when the second derivative is positive. So suppose that the second derivative is positive. So suppose we have f prime of a is equal to 0 and f double prime of a is greater than 0. So this indicates that the function is, oh, we just did that one. So the function is concave up, and so if the function, so this is just another way of looking at it. Okay, the second derivative is positive, means the original function f is concave up, which means the point has to be a local minimum. So the easiest way to remember the second derivative test is just to think about the concavity. When f double prime is positive, then the function's concave up, and if it's concave up and you have a critical point, it must be the minimum. So next, let's consider the case where f prime of a is equal to 0 and f double prime of a is less than 0. Now, similarly, the second derivative is negative, therefore it's concave down, therefore our critical point up here where the function has 0 slope must be a local maximum. So that's the short of it. To go into slightly more detail, well, the second derivative less than 0 implies that the first derivative must be decreasing, at least at the point A. So the first derivative, f prime, we know that f prime of a is 0, so it has to be decreasing through 0. So here's x, and here's a graph of f prime. So f prime, so therefore f prime goes from positive to negative as x passes through x is equal to a. So f prime was positive up here, and then it's negative down there. Now, whenever the function, the derivative is positive, the function is increasing, right? Positive derivative, the function is increasing. So the function f goes from increasing to decreasing as x passes through the point x is equal to a. So the function is going from increasing to decreasing, and then right here at the point A, it has 0 slope. It has to be a local maximum. So that's essentially what the second derivative test says and why it's true. Now, for the case in which it's inconclusive, so if f prime of a is equal to 0 and f double prime of a is equal to 0, so the second derivative test yields no information. So you might be tempted to say, well, if the second derivative is equal to 0, maybe that's a saddle. You know, like what we saw earlier with the function f of x is equal to x cubed. Well, here, this is a critical point at the origin, but it's neither a minimum nor a maximum. So f prime of x would be 3x squared. So clearly it's a critical point. F prime of 0 is equal to 0. F double prime of x is 6x. F double prime of 0 is equal to 0. So this says no information from the second derivative test. And you might be tempted to say, well, if the second derivative is 0, it's one of these cases where it's neither a min nor a max. It's increasing, levels off, then continues to increase. So it's not a minimum because the values for positive x are greater than this value. And it's not a maximum because the values to the left of this point are smaller than this value. So it's neither. However, in the case when we get the second derivative equaling 0, it's not necessarily true that it's a saddle point. So we'll call this a saddle point. So a saddle point, recall, is just a critical point that is neither a minimum nor a max. Or a max. So it's one of these ones that levels off and then keeps going up. So if you have a saddle point, then the second derivative will be 0 if it's continuous, if it's defined. But if the second derivative is 0, that doesn't necessarily mean you have a saddle point. So here's the counter example to that statement. So let's do a counter example. So f of x equals x to the fourth. Well, this one we know is a local minimum because it's positive everywhere except at 0 where it's 0. So it's something like this. So this is y is equal to x to the fourth. Right? So since it's x to the fourth, that's an even power of x, the output must always be positive. So at the point 0, you have to have a global minimum. So that's in fact our global minimum. It's also a local minimum because every time you have a global minimum, it must also be locally a minimum, right? You can't have something that's not locally a minimum, but it is a minimum globally. That doesn't make any sense. So let's see what the second derivative test gives us. F prime of x, 4x cubed. F double prime of x, 12x squared. So f prime of 0 is equal to 0, so we know it's a critical point, and f double prime of 0 is equal to 0. So the second derivative test is giving us no information. But you can see with this counterexample the danger in saying, well, if the second derivative is equal to 0, it must be a saddle point. This is not a saddle point, it's a bona fide minimum. So just because the second derivative is equal to 0 doesn't mean it's a critical point that's neither a min nor a max. It could be a minimum, it could be a maximum, or it could be neither. So you don't want to conclude when you see the second derivative equaling 0 that you have a saddle point. The second derivative equals 0 just says, second derivative test gives no information. So just say no info, and that's how you would do that.